Inside your computer are billions of units called transistors. These transistors serve a variety of purposes, but they commonly act as a sort of very small light switch. Each switch can be turned on or turned off. Computer scientists will often represent a switch that's turned on with the number 1, and a switch that's turned off with the number 0. These zeros and ones form a number system called binary, and it's the fundamental language of computers. From just these zeros and ones, we end up with computers that can perform calculations, create documents, view images, browse the web, and more. How does that happen? In this series, we'll explore the foundations of computer logic, starting from the fundamentals and building our way to more and more sophisticated systems. Using these switches, our computers can store information. Each switch stores a single bit of information, a 0 or a 1. But computers don't just store information, they process it, transforming inputs into outputs. That's where logic gates come in. Logic gates are the building blocks of computer circuits. They accept input and produce output according to a set of logical rules. One of the simplest logic gates is the NOT gate, represented graphically here. The NOT gate takes a single input, either a 0 or a 1, and inverts it, so that the output is the opposite of whatever the input is. If the input is a 1, then the NOT gate outputs a 0. If the input is a 0, then the NOT gate outputs a 1. To represent the logical rule this gate obeys, we can draw a truth table, which is just a way of writing down the rules for some logical formula. This table says that if the input is 0, then the output is 1. And if the input is 1, the output is 0. Often, though, our computers need to be able to perform calculations not just on a single bit of information, but on multiple bits of information. The AND gate, shown here for example, is a logic gate that takes 2 inputs instead of 1. Let's call these 2 inputs A and B. As the name might suggest, the AND gate will output a 1 when both A and B are 1s, but in all other cases, AND will output a 0. We can construct a truth table here too. This truth table is a bit bigger, since with 2 inputs there are more possibilities to consider. If A and B are 0, the output is 0. If A is 0 and B is 1, the output is 0. If A is 1 and B is 0, the output is still 0, and only when both A and B are 1s is the output a 1. The OR gate, meanwhile, is also a logic gate that takes 2 inputs. This gate outputs a 1 when A is a 1, or when B is a 1. So if both inputs are 0, the OR gate outputs a 0. But if either of the inputs is a 1, or both inputs are a 1, then the output of the OR gate is also going to be a 1. These logic gates on their own follow fairly simple rules, but they can combine with each other to form more complex calculations. Imagine what would happen if, for example, we took 2 inputs, passed them into an AND gate, and then passed that output into a NOT gate. What would happen? If both inputs are 0, the AND gate will output a 0, and the NOT will turn that 0 into a 1. If only one of the inputs is a 0, nothing changes. But if both inputs are 1, the AND gate will output a 1, and the NOT will turn that 1 into a 0. In other words, this circuit appears to do the opposite of whatever the AND gate on its own would do. It turns out that inverting the result of an AND calculation is such a common operation that it has its own logic gate, the NAND gate. This gate is equivalent to an AND followed by a NOT. So if the AND truth table looks like this, then the NAND truth table is identical, except all of the outputs are inverted. Whenever AND would output a 0, NAND outputs a 1. Whenever AND would output a 1, NAND outputs a 0. As you might guess, if there's a logic gate to take the opposite of an AND gate, there's also a logic gate that takes the opposite of an OR gate. This is the NOR gate. when both inputs are 0, OR would normally output a 0 too, so the NOR gate will flip that and output a 1. In all other cases, at least one of the inputs is 1, so OR would output a 1, and so the NOR gate will output a 0 instead. Let's now use these gates to solve a sample problem. Given two inputs A and B, we'd like to calculate whether exactly one of them is a 1. Well, what does it mean logically for exactly one of these two inputs to be a 1? Well, it means that either A or B must be a 1, but it also means they can't both be a 1. So logically, we might represent this as A or B, and not A and B, to mean that one of the two must be a 1, but both can't be a 1. We could create a circuit to perform this calculation too, but this circuit is starting to look fairly complex. So once again, there's a logic gate to solve this problem precisely. The exclusive OR gate outputs a 1 when exactly one of its inputs is a 1. So if only A is 1, or only B is 1, then the output of exclusive OR is 1. But otherwise, if both inputs have the same value, both zeros or both 1s, then the output is 0. And just for completeness sake, there's also a gate for inverting the exclusive OR gate, the exclusive NOR gate. This gate does the opposite of what exclusive OR does. While exclusive OR will output a 1 when the two inputs are different from each other, exclusive NOR will output a 1 when the two inputs are the same, both zeros or both 1s. These logical gates, NOT, AND, OR, NAND, NOR, exclusive OR, and exclusive NOR, make up the foundation of computation in computers. By combining just these few logical gates, each of which obeys a relatively simple logical rule, we can construct computers that can represent all of the data and perform all of the complex calculations that our computers do every day.
Okay, so what is up guys? At ngayon, pass muna tayo sa C++ programming. Move muna tayo sa basic logic gates ng computer assembly. Okay? So, bakit natin ito kailangan pag-aralan? Kasi kung gusto mo matuto mag-Arduino, at least kailangan mo muna gumamit nito. Kasi kasi sa Arduino, sa pagbuo, kung gusto mo makagawa ng robot, gusto mo gumawa ng mga RFID, voice-operated na ilaw, fingerprint scanner na door lock, so magagawa mo lahat yun gamit ang Arduino. So, isa ito sa mga pundasyon nun. So, ito yung basic logic gates, okay? So, isulat natin dito sa kapirasong papel na meron ako. Basic logic gates. So, ano nga ba ang basic logic gate? So, basic logic gate, ito yung parang ugat ng iyong computer, okay? So, ito yung nagpapasa ng 1010 ng binary na information, okay? So, yung logic gates, yun, okay? So, ang basic logic gates, meron tayong tatlo niyan. So, una dyan yung AND. Sunod ay NOT. Tsaka OR. Okay? So, si AND, okay? Ganito ang symbol niya. Dito muna tayo kay AND. Okay? Si AND gate. Okay? Si AND gate, ganito ang symbol niya. Yan. Okay? Para siyang letter D na merong dalawang buntot sa unahan tapos isa sa likod. And then, ang operation niya naman ay multiplication. Okay? Okay, dalawang parenthesis na ganyan. Multiplication yan, diba? Si OR gate, okay, si OR gate, ang ganito naman yung itsura niya. Ayan. So, ayan, para siyang piatos. Para siyang, basta triangle na medyo may curve. Yan. So, ang operation niya naman ay addition. Tapos, ang pinakauli sa ating basic na logic gate ay NOT gate. Okay? So, NOT gate. Okay, ano yung ginagawa ni NOT gate? So, ano muna yung symbol niya? Ang symbol niya ay ganyan. Triangle, tapos meron siyang bilog, tapos may buntot ulit. So, ano yung function niya? Ano yung symbol niya? Kasi ito, 'di ba? Multiplication, si AND gate. Si OR gate naman, addition. Si NOT gate, bar. Okay, bar. So, ano yung ginagawa ng mga bar? Halimbawa, X bar. Halimbawa, ang value ng X natin, 1. Okay, naka 1. So, ang kabaliktaran niya, wag nilagyan mo ng bar, magiging 0. Kasi sa binary, 1 at 0 lang naman, di ba? 1, 0. Kaya nga 1, 0, 1, 1, mga ganon. So, kung babaliktarin mo yung 1, edi 0. Eh, kung ang X mo naman ay 0, okay, nilagyan mo ng bar, magiging 1. Okay, babaliktarin mo lang. Okay, so, ngayon, ano naman tayo? Gawin natin yung kung paano ito gawa ng truth table. Okay, ngayon alam niyo na yung function ng tatlong basic logic gates, gawa natin siya ng truth table. So, paano natin gagawin yun? Kung mapapansin nyo dito, si AND gate, dalawang buntot. Si OR gate, dalawa yung buntot. Si NOT gate, isa lang. Bakit? Kasi, si AND gate, si OR gate, dalawa yung input niya, and then, isa lang yung output. Okay? So, dalawa yung input ni AND gate, isang output. Si OR gate naman, dalawang input, isang output. Si NOT gate, isa lang. Okay? Isa lang. And then tapos, ang output niya, isa din. Okay? Parang 1:1. Yung dalawa, 2:1. So, gawa natin siya ng truth table. Dito muna tayo sa AND gate. Halimbawa, meron tayong input. Okay? Dalawang input. A, B. Ang output natin ay C. So, ganito yan. So, lagi kayo magsisimula sa 0, 0, 1, 1. Kasi dalawa input natin eh. 0, 1, 0, 1. Since ang sinabi dito, si AND gate daw ay multiplication, si 0, mumultiply natin ng 0. 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. 1 times 1, 1. Okay? So, lagi nyo lang tatandaan, kapag nakakita kayo ng AND gate, kapag may nakita kayong 0, 0 na yun. Okay? So, isunod naman natin si OR gate. OR gate. So, ayan. So, meron ulit tayong dalawang input at isang output. Okay? So, lagyan ulit natin 0, 0, 1, 1, 0, 1, 0, 1. So, si OR gate, addition daw. Okay? Addition daw yung kanya. So, dito ulit tayo. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, ano sagot? 2. Hindi 2. Sa binary, kapag 1, 1 pa rin. Kasi 1 at 0 lang naman eh, okay? So, eto na. Ngayon, marunong na tayo ng truth table ng AND gate at ng OR gate. So, sunod naman natin ay yung NOT gate. Okay, NOT gate. Sabi dito sa drawing natin, isa lang ang input, isa lang din ang output. Okay? So, A, B. Kita niya? So, ayan. Since isa lang ang input natin, ganito lang yan. 0, 1. Yun lang. So, ano yung output nito? Sabi sa NOT gate, babaliktarin mo daw. So, 0, kabaliktaran ng 0, 1. 1, kabaliktaran ng 1, Okay? Kabaliktaran ng 1, 0. O, yun na yan. Okay? So, ganun lang kasimple yun. Ganun lang kasimple yung truth table ng logic gates. Okay? Ng basic logic gates. So, bakit ito basic logic gates? Kasi meron pang ibang gates. Mas mahirap pa. So, saka na natin pag-usapan yun. Nakakalito yun, promise. Okay? So, lagi nyo natatandaan dito, kapag may 0, 0. So, kapag AND gate, kapag may 0, 0 na. Kapag OR gate, kapag may 1, 1 na. Okay? Kapag naman NOT gate, babaliktarin mo lang. Okay? So, guys, ngayon, marunong na tayo ng basic logic gate. So, susubukan naman natin siya i-apply ngayon, okay? So, gagawa tayo ng problem. A plus B. Okay, A plus B times AB bar. Okay, not AB. Okay, so paano natin ito sasagutan? So, unahin natin, gawa natin ng diagram, okay? So, A plus B. A, B. Dalawa lang. Ibig sabihin yan, dalawa lang input. Okay? So, ayan. So, ano yung symbol ng AND gate natin? Meron tayong parang, ay, ng OR gate natin, na meron tayong parang triangle. So, gagawin natin triangle. Ayan. So, bakit mahalaga to? Kasi ito yung magiging basis mo eh, mamaya eh. Kung paano mo ilalagay yung mga wires mo. Okay? So, meron na tayong A plus B. Ayan, A plus B. So, sabi dito, kailangan ulit natin ng A tsaka B para ipagta-times natin. Kasi magkadikit eh, ibig sabihin, ta-times natin. So, habaan natin to. So, kukuha tayo dito ngayon ng A. Yan. So, lalagyan nyo ng pag ganun. Kasi lumaktaw siya. And dito ay B. So, ito ay A. Ito naman ay B. Okay? Gets? Ito ay A. Ito ay B. So, ibaba lang natin. Since multiplication siya, kasi magkadikit, ang logo na gagamitin natin ay itong parang letter D. So, letter D. Ayun, nalimutan natin lagyan ng buntot. Yan, may buntot. Output. So, kung makikita nyo, nakalagay siya sa parenthesis. Ibig sabihin, multiplication ulit. Ayan, may multiplication dyan. So, ito ay AB. Okay. So, bago natin i-multiply, huwag natin kakalimutan na meron tayo ditong NOT. So, paano yun? Okay. Si NOT, ang symbol niya ay triangle, tapos bilog. So, inanat muna natin yan. Okay, yung sagot niyan, hanap natin. And then, siya yung i-multiply natin dito. Okay, nagets ba? So, si AB, pinag-times. Nung ninat na natin, ito ay AB not. Okay, itong part na to, AB not. So, itong part na to, AB. Okay. So, itong part naman na to, ito na yung A plus B times AB not. Okay? Kasi A plus B tapos AB not. Pagta-timesin na natin. So, ayan. So, C output ay letter C. Okay, gets ba? So, gawa naman natin siya ngayon ng truth table. So, truth table. Pagpasensya nyo na isulat ko, maliliit at pangit din. So, A, B. Since dalawa lang yung input natin, 4 lang dapat ang ating binary. Okay? So, una dyan, meron tayong A plus B. Okay? So, A plus B muna tayo. A plus B. So, ano nga ba ang A plus B ulit? Ano yung A plus B? So, kapag A plus B, Kapag may 1, 1 na. Okay? So, 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. Okay? So, meron tayo niyan. Iwan muna natin yan. Sagutan muna natin tong AB. So, AB. Okay? So, A times B naman daw. Ito yung kapag may 0, 0 na. Okay? So, 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. 1 times 1, 1. Okay? So, ngayon, sabi dito, nakanot daw siya. Kailangan natin baliktarin. So, gagawa tayo rito. AB na may bar sa taas. So, ito yung not. Babaliktarin lang natin tong part na to. Itong AB kasi sagot na to eh. 1, 1, 1, 0. Okay? Kita nyo, binaliktad lang natin yung sagot. So, ito na yung final answer. Si A plus B, ito times natin sa AB. Okay? Times natin siya sa not AB. Okay, so times na daw natin. 0, 1. Okay, 0 yon. 1 times 1, 1. 1 times 1, 1. 1 times 0, 0. So, ito na yung final answer natin. Okay, so, bakit mahalaga to? Napaka-importante na tama yung gagawin yung truth table kasi ito yung gagamitin nyo sa pag-check mamaya ng kung tama yung placement nyo ng wires sa inyong breadboard, okay? So, ayan. So, i-introduce ko na ngayon kayo sa breadboard, okay? Okay, guys. So, ito yung tinatawag na breadboard, okay? Okay, so ipapakita ko sa inyo yung kung ano yung nasa loob ng IC na 7404 which is yung NAT, okay? So, eto siya. So, makikita nyo dyan, meron tayong isang input, isang output. Okay? Tapos, makikita nyo dun sa may pinakadulo, meron tayong positive. Okay? And then, sa pinakadulo naman sa baba, meron tayong negative. Okay? So, dun yung supply ng power natin. Okay? So, ito yung kay AND gate. Ito naman yung kay AND gate. Meron siyang dalawang input, isang output. Tapos, sa upper right niya, upper left, meron diyang makikita nyo na positive. So, power supply yan. Sa baba, sa lower right, merong negative. Ganon din kay OR gate kasi dalawa rin yung input niya and then isang output. So, meron tayong isang positive sa taas and then negative sa baba. Yun yung power supply niya rin. Okay? So, yan, nakita nyo na yung diagram. Ngayon, bakit ko iniwan to? Bakit ko itinabi to? Kasi, itatry natin siya ngayon i-plot. Okay? Itatry natin i-plot. So, mag-drawing muna tayo dito ng IC para mas madali. Ganito kasi yung ginagawa kong technique para mas madali kong ma-plot yung mga wire. So, si IC ay merong 7 pin. Okay? Ayan. 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 So, 74, 04, or not. Okay? Ito naman. Ano pa isa pa? Sensya lang paano ang drawing ko. Okay? Ayan, may 7 pin din. So, ito yung positive, negative. Positive, negative. Okay? So, not ito naman ay negative. So, 74, 08. And then, ano isa pa? 74, 32. Okay? So, lagyan natin ng tigol ng, dito na pin. Okay, so meron na tayong, positive, negative. So, meron na tayong drawing ng IC. So, ayan o. Titignan nyo, tig 7 pin din yan. 1, 2, 3, 4, 5, 6, 7. Ito yung negative. Tapos 7 din dito. Ito yung positive. Yung dulo, okay? So, mamaya na yan. So, sabi dito sa ating drawing, meron tayong A plus B. So, sino ba dito yung plus? Diba ito? Plus yan. Ito ay multiplication Ito naman ay bar. Okay? So, ayan, plus. So, sabi, A plus B. So, dito lalagyan natin si A, then si B. Kasi nga, input. And itong pangatlo, ito yung magsisilbi niyang output. Kagaya nung nasa drawing. Kung nalimutan nyo, pwede nyo i-back yung video. Okay? So, si output niyan, tatabi lang muna natin. So, si A at B ulit. Okay? So, si A at B, kukunin natin si A at B. Lalagay natin sa end. Bakit? Kasi, kailangan natin ng A at B para dito sa multiplication. Mamaya pag plinat natin to, mas magigets nyo. Masaya to. Ayan. So, itong input natin ito ay A. Ayan ang susundan nyo. Ito naman okay, so ipa-plot na natin siya ngayon. So, ito yung ating drawing kung paano siya dapat i-plot. And then, nandito yung ating IC. So, kita naman pala, no? So, ito yung 04. Ay, lumabo ulit. Hayaan na nga natin yan. So, meron tayong drawing dito. So, dyan tayo magbe-base ngayon, okay? So, ano yung mga kailangan natin? Kailangan natin ng breadboard. Itong kulay white na to. Magkano to? 120 pesos lang to. And then, ito naman ay mga IC. Ayan, so IC ng 7404, 7408, 7432. So, 30 pesos lang isa niyan. Then, ito naman, battery. Mga 50 pesos to 70 pesos. Tapos ito, 10 piso lang ata itong takip na to, battery cap. Battery snap. Snap daw tawag dito, hindi daw cap. Ayan. So, balik natin. Okay. So, syempre, mga jump wires. Okay. So, ito, 5 pesos isa na ito. Medyo may kamahalan. Syempre, ito yung ating LED light. Magkano to? 3 piso lang. Okay. So, ayan. So, magpa-plot na tayo ngayon according sa ating drawing. Okay? So, lagyan natin ito sa baba kasi matatabunan ito mamaya ng mga wire. Okay. So, lagyan muna natin itong mouse ko dyan. So, una, input tayo ng A at B. So, kunin natin itong red. Itong red, ito ang ating A. So, yung kabilang side niya, itabi muna natin kasi hindi pa naman natin ginagamit. And then, si B, may kulay brown. Okay, brown. Si B ay kulay brown. Tabi lang din natin yung isa niyang So, makikita nyo, dalawang input. Okay, kagaya dito, dalawang input. And then, yung output niya, may natin kulay green. So, yung output niya, dito sa pangatlo. Kagaya nung nandito sa drawing, nasa pangatlo yung output. Si output, itabi lang muna natin dito kasi hindi pa naman magagamit. Yan. So, ang sunod natin, kailangan daw natin ng AND gate. Okay? Kasi, magta-times nga tayo, di ba? Dito, magta-times tayo. Okay? Ito na yung ginawa natin, A plus B. Kasi si 32 plus yan, di ba? So, 08 times. So, gagawin natin to. So, saan tayo kukuha ng A? Tsaka ng B. Di ba may hindi tayo ginamit na A? B. So, yun yung ilalagay natin dyan. A. Yan ito, si B. Pangalawa. Okay. Yan. Napakaganda. So, kailangan natin ng output. Kuha tayo ng isa pa. Kulay orange. Lagyan natin yung orange dito. Okay, so meron na tayo ngayong, ayan o, kagaya niyan, kumuha tayo, nilagay natin sa A, and then yung B, ayan, sa pangalawa. Okay, tapos si output niya, kailangan daw naka-NOT. Kagaya nga ng sabi dito, yung output ng A tsaka B, naka-NOT. Okay, so ilalagay natin sa NOT. Ayan o, si A at B, ninat natin, di ba? Binaliktad natin. So, dinala natin siya ngayon sa unang slot ng NOT. So, isang input lang yon. Ang output niya, isa lang din. Ayan. So, ito na yung NOT AB. Baliktad na. Okay? So, itabi natin. So, meron na tayong NOT AB. Meron na tayong A plus B. Okay? So, ito si NOT AB. Ito si A plus B. Okay? Si yellow at si green. Okay, so ayun. So kung makikita nyo, okay, hindi pa umiilaw kahit nalagay na natin yung sagot. Bakit? Ba't hindi pa umiilaw? Hindi pa nakakabit yung battery.
Gago!
Okay, so dito sa drawing natin meron tayong mga power supply. Okay, positive, 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 negative, negative, negative. So ilalagay natin siya. Dito makikita nyo meron tayong guhit. Okay, so isang line yan. Isang line din dito sa baba. Dalawa yan, o, dalawa. So, magkaiba yan. Hindi yan magkadugtong. Isang guhit yan, hindi pa ganon. Pa ganito yan. So, itong nasa taas na baba, itong part na to, ayan yung guhit niya. Yan yung gagawin nating negative. Ito naman, ito yung positive natin. So, itusok lang natin to. Lagyan natin sa negative. And then, ito naman, lagyan na natin sa positive. So, ayan, may power na tayo. Dito pa lang, sa unang IC na to. So, lagyan na rin natin itong iba. So, negative. Positive. Dito ulit, sa pinakadulo. Okay. And then, negative ulit. Positive muna natin. Positive. And then, negative. Tama ba yung pinaglagyan ko? Masyado makita. So, hindi pa rin nailaw. Kasi, wala pang battery. So, si red, positive, black, negative. So, yun natin, tusok natin yan dyan. Wait lang ha. Red, positive, black, negative. Makikita nyo, umukurap na, diba? So, yan. Maluwag lang. So, umilaw na siya. Okay? So, ibig sabihin, may connection na. Ngayon, di pa natin alam kung tama yan. Diyan papasok ngayon yung truth table natin. Okay? So, ito yung sense ng truth table. Kung bakit napakahalaga ng truth table. Okay? So, gagamitin natin itong dalawang wire. Lalagay natin yan dito. Sa ilalim ng A. Ito yung magsisilbi natin pan-check. Itong blue ay yung A. So, lagay natin yan dito sa A. Sa unang input natin. Matay, di ba? So, ito naman ay B. Okay? So, sabi, kapag daw 0, kapag parehas negative, ang output niya ay, ang ilaw niya mamamatay. So, kapag parehas na nilagay natin to sa negative, itong wire na to, mamamatay ilaw. So, ilagay natin to dito. Negative to, diba? So, negative si B, negative si A, namatay ilaw. Kasi 0, 0, negative parehas, patay. So sabi, kapag 0 daw si A, 0 si B, 0, patay ilaw. Kapag 0 si A, 1 si B, hindi ilaw. So check natin, lagyan natin si A sa positive. So umilaw. So try naman natin na si A yung nasa negative, ay yung okay, ayan, tama na pala to. Positive si A, then 0 si negative. 0 si negative. 0 si B. Ayan yung ginawa natin. So ayan, brown nasa negative, A nasa positive. So baliktarin naman natin. Iilaw pa rin. Ito na yun. 0 si A nasa negative, si B positive kasi nasa positive line siya. So try naman natin para sila nasa positive. Ano mangyayari? Namatay. Okay, so ito yung basic ng sa digital logic gates. Okay, so magiging stepping stone to para sa pag ano natin na Arduino. Okay, so kung marami pa kayong gustong matutunan, huwag niyo kalilimutan mag-subscribe sa channel na to at ayun, i-click nyo notification bell para updated kayo. At yun, like nyo na rin yung video kung may natutunan kayo. At salamat sa pakikinig. Yun lamang. Bye-bye. Peace out.
Let's begin our discussion with binary numbers. Now, when you hear the word bi, what do you think of? Bi is associated with the number 2. And so binary numbers have only two possibilities, 0 or 1. Now, when dealing with circuits, 0 is, or it corresponds to a circuit being in the off state. 1 corresponds to a circuit being in the on state. So if you're dealing with true and false statements, an off state will be considered false, and on state would be considered true. If you're dealing with voltage, an off state would have 0 volts, and an on state, typically 5 volts, but something other than 0. Now, before we go over and, or, and not gates, let's talk about the buffer gate. So here is the symbol of the buffer gate. And it basically looks like a triangle pointing towards the right. On the left, we have the input. On the right, we have the output. So we're going to call the input A. The output will also be the same. So if we were to make a truth table with the input and the output, if the input is on, which means it has a binary number of 1, the output will also be in the on state. If the input is in the off state, which means it has a binary of 0, the output will have the same binary number of 0 as well. Now let's draw a circuit to represent this. And the principal element of this circuit will be an NPN transistor. This is the base, this is the collector, and this is the emitter. Now we're going to connect this to a power source, and we're also going to use a light emitting diode. Now the light emitting diode, it's going to represent the output of the circuit. Now let's connect this to a voltage source. So here is the input, which we'll call it input A. And what's going to happen if we apply a voltage to point A? So if the input is in an on state, will the LED, will it be on or off? Well, once you apply a voltage to the base, the transistor will turn on. Current will flow from the collector to the emitter. Therefore, the LED will be in an on state. So this corresponds to a 1 for the input and the output. Now, what about if the input is off? So in this case, we have a 0 at the input. If there's no voltage at the base, then the transistor will be off. no current will be able to flow from the collector to the emitter. So therefore, the LED will be off as well. And so that's basically the buffer logic gate. So if you have a 1 in the input, you're going to have a 1 in the output. If you have a 0 in the input, you have a 0 in the output. Now the next type of logic gate that we're going to talk about is the NOT gate. So here is the electrical symbol for it. It looks like a buffer gate, but it has like a circle in the front. Now let's call the input A. The output will be the complementary of A. You can also write it as A bar. Now let's write a truth table. So we're going to have the input and the output. So if we have a 0 at the input, the output will be a 1. And if we have a 1 at the input, the output will be 0. It's always going to be the opposite. So basically, if the input is in an off state, the output will be in an on state, and vice versa. Now, how can we represent this using a transistor circuit? The circuit is going to be very similar to what we drew before, but there's going to be one key difference, and that is the location of the LED. So here is our voltage source, and on the left we have our input A. The emitter is attached to the ground, but the LED will be connected across the collector of the transistor and the emitter. So once again, this will be our output. So let's say if the circuit, or rather input A, is in the on state. Will the LED be in the on state or the off state? Well, let's analyze it. So once we apply a voltage to the base of the transistor, current will be able to flow from the collector to the emitter. So current will flow from the positive 5 volts through the resistor. Now, once it gets to this point, it has two options. The current can flow to the right or it can flow to the left. Now, electricity will will always take the path of least resistance. And if the transistor is on, then the path of least resistance is from the collector to the emitter. So therefore, no current will flow in this direction. So this will be in the off state because the current has been diverted through the transistor. So notice that we have a complementary situation. The input is on, but the output is off. Likewise, the reverse is true. So let's say that the input is off. There's no voltage applied at input A. So what's going to happen? Current will still flow through the resistor. Now, once it reaches this point, because the transistor is off, it cannot flow through the transistor. So therefore, it has no choice but to flow through the LED. So therefore, the LED is in an on state. So as we can see here, if we have a 0 at A, the output will be a 1. And if we have a 1 at A, the output is a 0. And so that's the basic function of a NOT gate. It turns an off state into an on state and vice versa. It turns A into A prime. Now the next logic gate that we're going to talk about is the AND gate. And here is the symbol for an AND gate. We're going to have two inputs, A and B, and the output will be A times B. Now let's write a truth table. And at the same time, let's draw a circuit for this. So we're going to need two transistors as opposed to one. So this is input A, and this is input B. And let's connect it to a voltage source. So what happens if input A and B are in an off state? Will the LED be on or off? In this case, both transistors will be off. So no current can flow from the positive 5 voltage source to the ground. So therefore the output will be a 0 because the LED is off. Now what if A is in an on state and B is in an off state? Will the LED be on or off? Current can flow through the resistor, through the LED, and through the first transistor. However, because the second transistor is off, no current can flow through it. So therefore, no current will flow through the LED. So the LED will be in an off state. So we're going to put a 0. The only way the LED can be on is if both inputs A and B are on. Only under that circumstance can current flow through the LED and through both transistors to make it to the ground. So thus we have the word AND. The only way the output can be in an on state is if both inputs A and B are on the on state. So even if B is on and A is off, no current will flow through the LED. Only if A and B are on. Now let's move on to the OR circuit. And let's begin by drawing the symbol for that. So here's how it looks like. So let's say this is input A and B. Now it's not going to be A times B as in the case of an AND circuit, but it's A plus B for the OR logic gate. Now let's make a table just like before. And let's draw a circuit that corresponds to it. So this time what we're going to have is 2 NPN transistors. But they're going to be connected parallel to each other to make the OR logic gate. In the case of an AND logic gate, they were connected in series with each other. And so that's the key difference between the AND and the OR logic gate. Now let's say that transistor A and B are in the off state. Will the LED be on or off? So clearly, no current can flow through the first transistor or through the second transistor. So therefore, no current will flow through the LED. The LED will be off. So we can put a 0 in the truth table. Now what about if the first transistor is on, but the second one is off? What's going to happen? Current can flow through the resistor, through the LED, but through the transistor that is on. So therefore, there's a path from the positive voltage source to the ground. So the LED will be on. So let's put a 1. Now what if transistor B is on, but transistor A is off? Current can still flow, but this time through transistor B. So the LED will be on. Now what if both transistors are on? In this case, the LED will definitely be on. Current can flow through transistor A or through transistor B. So thus we have the OR logic gate. The LED will be on if A or B is on. And so that helps me to remember the truth table for the OR logic gate. If we have a 1 in A or B, doesn't matter which one, the output will be on. Now, I want to talk about the NAND gate, but let's compare it with the AND gate. The NAND gate is basically the complement of the AND gate. So here is the symbol for the AND gate. The NAND gate symbol looks very similar. The only difference is we're going to have a circle at the end. So let's say this is input A and this is input B. The output of an AND gate, we said it's A times B. For a NAND gate, it's going to be the complement of A times B. Now remember, the complement of a 0 is 1, and the complement of 1 is 0. Now let's look at the truth tables for these two types of gates. So as we recall, the only way to get a 1 with an AND gate is if both inputs A and B have a 1. Besides that, it will be a 0. In the case of a NAND gate, when both inputs A and B are on, the output will be off. So as you can see, this column rather, is the complement of this column. Now, we could use an AND gate and a NOT gate to construct a NAND gate. So here is the AND gate, and let's put a NOT gate next to it. So let's say this is input A, input B. The output of an AND gate is AB, and once you use a NOT gate, it basically takes the input and gives you the complement of that. So the complement of AB is just AB prime. And so the combination of these two logic gates will produce, or is equivalent to, a NAND gate. Now here's a question for you. Let's say if we have a NAND gate, and let's say if we take the two inputs of a NAND gate and connect them together. What type of logic gate do we now have? What would you say? So let's compare it to the original NAND gate. So this would be A and B, and we would get A times B, but the complement of that result. Well, now we only have one input because both of these will be A. And so if we multiply these two, it would be A times A, and then we'll get the complement of that. What is A times A? Now you need to be familiar with some rules of Boolean algebra, and we're going to go over those rules soon. But A times A is basically A. One way to help you to see this is if you multiply 0 and 0, you get 0. If you multiply 1 and 1, you get 1. Now keep in mind, we're dealing with binary numbers. And so in a binary system, it works out to be true. A times A is A. So this is the same as the complement of A. So notice that we went from A to A prime. This is the equivalent of a NOT gate. So that's how you could use a NAND gate to make a NOT gate. So these two are functionally equivalent. Now, let's understand how this works using a truth table. So let's write the truth table of a NAND gate. Now, once we connect the two inputs together, let's say once we make this circuit, here we have this circuit, by the way. These two columns has to be the same. So therefore, these two possibilities cannot work. Because let's say if this is A, this has to be A as well. So meaning, let's say if we have a 1, we can't have a 1 and a 0. That's not possible. It's either, if this is going to be a 1, both of these inputs will be a 1. Or if we have a 0 here, both inputs will be a 0. So these are the only two possibilities. So if we have a 0, the output is a 1. And if we have a 1, the output is a 0. And so this is the same table of a NOT gate. Now let's talk about the OR and the NOR gate. The NOR gate is the complement of the OR gate, much in the same way as the NAND gate is the complement of the AND gate. And so let's draw the symbols for both of these. The NOR gate looks like the OR gate, but with a circle at the end. So given inputs A and B, the output of the OR gate, we said it's A plus B. For the NOR gate, it's going to be A plus B, and then it's the complement of that result. Now let's write out the truth tables. The OR gate, the output of an OR gate will be in the ON state if either A or B is in the ON state. Now, in the case of the NOR gate, it's simply the reverse. If either A or B is in the ON state, the output will be in the OFF state. Now, one of the first things that you need to be able to do if you're taking a course in Intro to Logic Design is that you need to be able to write a function given a block diagram. So let's start with the first one in the upper left corner. The first thing I like to do is identify what type of logic gates I'm dealing with. So this is an AND gate. I'm going to use a capital A to represent it. Now, for the over here, notice that the inputs of the first AND gate are A and B. And when dealing with an AND gate, you need to associate it with multiplication. And when dealing with an OR gate, associate it with addition. So what the AND gate is going to do is going to take the two inputs and basically multiply them together. So the output will be A times B. Now the second AND gate will take this input, which is AB, and multiply it by this input, which is C. So thus we could say that the output of this entire circuit, represented by function f, is going to be the product of A, B, and C. So this is the answer for the first one. Now what about the second one in the upper right corner? Feel free to pause the video if you want to try it yourself. So let's begin by identifying each logic gate in the circuit. So we have two AND gates, and here we have an OR gate. So the output of an AND gate is going to be basically the product of the inputs. So this is just going to be X times Y, and here the inputs are X and Y prime. So this is going to be X, Y prime. Now the OR gate is going to take the two inputs and then it's going to add them together. So the output of the OR gate will give us the function xy plus the other input xy prime. And so we could say that function f is equal to xy plus xy prime. So that's how we can write the function using or given a block diagram. Now let's consider the third one on the bottom left. So this is an AND gate, and so is this one, and here we have an OR gate. So when dealing with an OR gate, we're going to take the two inputs and add them together. So this is going to be A plus B. And for the AND gate, we're going to take the two inputs and multiply them together. So this is A times B prime. Now here we have another AND gate, so we're going to take these two inputs, multiply them together. So we may need to use a set of parentheses. So the function is going to be A plus B, so that's this input, times A B prime. You could put that in parentheses if you want to, but you really don't need to. Now let's focus on the last one. We have one AND gate and two OR gates. So for the first OR gate, we're going to take the two inputs and add them together. So this is going to be X plus Y. And for the second one, we're going to do the same thing. So this is going to be X prime plus Z. Now for the AND gate, we're going to take these inputs and then multiply them together. So in parentheses, we have the first one, X plus Y, and then times the second one, X prime plus Z. So F is equal to what we have here. Now, here is a challenge problem. Go ahead and write the function given the block diagram shown below. Feel free to take a minute and work on this one. So let's identify the logic gates that we have. So here we have an AND gate, an OR gate, another AND gate, and then we also have an OR gate at the right. Now let's focus on the first AND gate. We're going to take the inputs X and Y, and we're going to multiply them. Now for the OR gate, we are going to add XY with the other input Z. So this will be XY plus Z. Now for this AND gate, we are going to multiply these two together. So it's going to be X prime times XY plus Z. Now, let's talk about the AND gate at the bottom. This is a 3-input AND gate. And the output of that AND gate is simply going to be the product of the 3 inputs. And so that's going to be X times Y prime times Z. Now the last thing we need to deal with is the OR gate. And this is a 3-input OR gate, and all we need to do is add the 3 inputs together. So anytime you're dealing with an OR gate, think of addition. When you're dealing with an AND gate, think of multiplication. So we could say the function f, the output of it, is going to be the first input, which is x prime times xy plus z, plus the second input, which is w, plus the last input, which is x, y prime, z. So this will give us the output of this circuit diagram using the inputs that we have here. So that's how you can write a function given a block diagram. Now let's work on the reverse. Let's say if we're given a function, how can we draw the block diagram? Let's say the function is ab plus c. Go ahead and draw the block diagram for that given function. So first, notice that a and b are multiplied to each other. So we're going to deal with an AND gate. And notice that we have an addition symbol. So we're going to use an OR gate between A, B, and C. So let's begin. Let's start with the AND gate. So here are the two inputs, A and B, and then the output of that will be just AB. Now we need to connect that with an OR gate. And then we need a new input, input C. So the OR gate will take the sum of these two inputs, and so we'll get the output AB plus C. And so that's it for that example. Here's another function. Let's say we have f is equal to xy plus x prime y plus y prime z. So go ahead and draw a block diagram for that given function. So notice that here we have what is called a product term. So we're going to use a AND function for this product term. Here this is another product term. So we're going to use another AND function to connect x prime with y. And we need another one to connect y prime with z. So we need 3 AND logic gates. Now we could use one OR gate to basically add the 3 AND logic gates together. Because we have the plus symbol or a sum, we need to use an OR gate. So this is going to be the first AND gate, and we're going to put x and y together, and so that will give us the output xy. And then we're going to use another AND gate, and we're going to have the inputs x prime y, and then another one. So this is going to be y prime and then z. Now we're going to feed these 3 AND gates into an OR gate. And so the output of the OR gate is going to be the sum of the 3 inputs. And so that's how we can draw a block diagram for this expression. Now, something else that you need to know. This expression here is something known as an SOP expression, which stands for sum of products. XY is a product, as mentioned before. X prime y is a product, and y prime z is a product. So we have 3 product terms, and we're adding them. So that's a sum of products expression. Now, another term you need to be familiar with is literals. So every variable that you see, whether complemented or uncomplemented, is a literal. So x is a literal, y is a literal, x prime is 1. So we have a total of 6 literals in this expression. Now let's consider another example. So let's say that f is going to be a plus b prime, and then times a plus b plus c times b prime plus c prime. Go ahead and draw a block diagram. Now the last example was a sum of products example. This one is known as a POS, which is product of sums. This right here is a single sum term. The reason why it's a sum term is because you're adding a and b prime. So notice that we have a total of 3 sum terms, and we're multiplying each of those 3 sum terms together. So thus it is a product of sums expression. Now how many literals do we have in this problem? So we have 1, 2, 3, 4, 5, 6, 7. So there's a total of 7 literals in that expression. Now let's go ahead and draw the block diagram. Now, for a sum term, should we use an AND logic gate or an OR logic gate? What would you say? Now remember, you want to associate OR with addition or sums, and you want to associate AND with multiplication, or basically products. So because we have a sum term, we're going to use an OR logic gate for each one. So we're going to need 3 OR gates, and we're going to feed these 3 OR gates into a single AND gate because we do have multiplication here. So let's go ahead and draw the diagram. So let's start with our first OR gate. This is going to be a 2-input OR gate based on what we see here. So the first input is going to be A, the second one is going to be B prime, and the output of this OR gate will be A plus B prime. Now moving on to the second OR gate, it's going to be a 3-input OR gate. The inputs will be A, B, and C. The output is going to be A plus B plus C. And for the last OR gate, this is a 2-input OR gate with the inputs B prime and C prime. So this is going to be B prime plus C prime. Now let's feed these 3 OR gates into a single AND gate. So the output of this AND gate is going to be the sum, not the sum, but the product of these 3 expressions. And so you just got to multiply them. Thus is going to be everything that we see here. So I'm not going to write it again. And so this is the block diagram for the function f. Now let's work on number 3. Describe each of the following expressions as an SOP expression, sum of products, or POS expression, product of sums, both or neither. And at the same time, discuss the number of variables, literals, product terms, and sum terms, and identify any min or max terms. So let's start with this one. Let's say we have the expression xy prime plus xyz prime plus x prime yzw plus x y prime z prime. So is this a sum of products expression or a product of sum expressions? Or is it both or neither? So this is a product term. Each one of these are product terms. Now, just to review, one literal could be a product term. So x is a product term. Y prime is a product term. Or if you multiply them, these are product terms. So what we have here is a sum of products expression. We have 4 product terms, and as we can see, there's a plus sign separating them. So it's a sum of products expression. Now, how many different variables do we have in this expression? Notice that we have x, y, z, and let's not forget w. So we have a total of 4 different variables. Now, how many literals do we have? So here we have 2 literals. It could be complemented or uncomplemented. Here we have 3 literals. This has 4, and then this is 3. So if we add them together, there's a total of 12 literals in this expression. Now, what about if we have a min term or a max term? What would you say? In this case, since we're dealing with an SOP expression, a sum of product expression, we need to identify the standard product terms or the min terms. Now, a midterm is basically a standard product term that includes each variable of the problem. So it has to include all 4 variables, either complemented or uncomplemented. So this term right here is the min term in this expression because it has all 4 variables. Now let's move on to our next example. Consider this expression, x plus y times x prime plus z, and then times y plus z prime times x plus y plus z prime. So is this a sum of products expression or a product of sums expression? So x plus y, this is a sum term. X prime plus z is also a sum term. So notice that we have a total of 4 sum terms, and each of them are multiplied to each other. So this is going to be a product of sums expression. We have the product of 4 sum terms. Now, how many variables do we have in this expression? So I see 3 variables, x, y, and z. Now, how many literals are there in this expression? So here we have 2 literals in the first sum term. The second sum term has 2 literals. The third one has 2. And the last sum term has 3 literals. So thus we have a total of 9 literals in this problem. Now we're not going to have any min terms because this is not a sum of product expression. But we do have a max term because this is a product of sums expression. So what is the max term in this particular problem? So which sum term includes each variable of the problem, either complemented or uncomplemented? So this is the sum term that has all the variables. So therefore this is considered the max term. Now let's move on to our next example. Let's say we have the expression x, y prime, z, w. So this expression, is it an SOP expression, a POS expression, both, or neither? What would you say? It turns out that this is both a sum of products expression, and you could describe it as a product of sums expression. So in terms of, let's say, SOP, we could say that this is the sum of one product term. Now, in the case of a POS expression, you can also describe it as the product of 4 sum terms. Now, if that statement confuses you, see it this way. X, you could think of x as x plus 0. Y prime, you could see it as y prime plus 0. And then z plus 0 and w plus 0. Now, in this form, it looks more like a product of 4 sum terms. At least that's one way I think of it. But that particular expression can be described as both a SOP and a POS expression. Now, how many variables do we have? And how many literals? So for this expression, we have a total of 4 variables, w, x, y, and z. We also have 4 literals, w, x, y prime, and z. So that's all we could say about this expression. Let's move on to our next example. Consider the expression a plus b plus c prime plus d plus e prime. So can we describe this as an SOP or POS expression? Like the other example, you could represent it as both POS and SOP. So as an SOP expression, we can say that this represents the sum of 5 product terms. And as a POS expression, we could say that this represents the product of one sum term. So imagine if we put it inside a single set of parentheses. In this case, this would appear as one sum term. Now, it's important to understand that if you have just one literal, let's say it's either x or y prime, one literal can be considered a product term or a sum term. So just keep that in mind. Now for this particular example, we have a total of 5 literals: A, B, C prime, D, and E prime. We also have 5 variables: A, B, C, D, and E. And so that's it for that expression. So make sure that you understand the difference between a product term, a sum term, and a literal. So a product term could be just a single variable x, it could be y prime, or it could be multiple literals multiplied to each other, like xy prime or xyz. So those are product terms. A sum term can be an individual literal. It could be x, it could be z prime, or it could be a sum of multiple literals like x plus y, or even x plus y prime plus z. So those are sum terms. And a literal is just a variable. It could be x, y prime. It could be complemented or uncomplemented. So that's a literal. Now let's consider one more expression. Let's say we have A multiplied to B plus C D prime. What type of expression do we have? So here we have a single term, like a literal, and this is a product term. And it looks like just a mixture of SOP and POS. It turns out that this expression is neither. It's neither a sum of products or a product of sums expression. Now, this expression has 4 variables. As we can see, it's A, B, C, and D. And it has 4 literals. If we list them, it's A, B, C, and D prime. And that's all we can say about this expression. So this is an example of an expression that is neither SOP or POS. Now let's say if C wasn't there. What type of expression will we have now? Would you still say it's neither? Because this is now a sum term. When you have C here, this is no longer a sum term. But when you take away C, now we have a sum term. And A is considered a sum term. You can write that as A plus 0. So that's a sum term. And then B plus D prime. That's another sum term. So this is the product of 2 sum terms. So this would be a POS expression. But once you put C into the mix, this is no longer a sum term, nor is it a product term. So this would be neither. Now let's review some basic rules of Boolean algebra. Now whenever you see a plus sign, know that you're dealing with the OR logic gate. And if you see like multiplication or a product term, Remember, you're dealing with the AND logic gate. So the first law that we're going to go over is the commutative property. A plus B is the same as B plus A, and A times B is the same as B times A. The next one is the associative property. So A plus B plus C is the same as A plus B plus C. And A times BC is the same as AB times C. So that's the associative property. And as you can see, the order for the and or operators doesn't matter. The next one is the identity rule. A plus 0 is equal to A. And A times 1 is also equal to A. The next one is the null property. A plus 1 is equal to 1, and A times 0 rather, is equal to 0. Now, if you're analyzing this using old school algebra, this equation might make sense to you, but this one might be a little confusing. For instance, if A is 0, 0 plus 1 equals 1. Okay, that makes sense. But what if A is 1? 1 plus 1, does it really equal 1? Well, in old school algebra, 1 plus 1 is 2. But when dealing with Boolean algebra, 1 plus 1 does equal 1. And let's prove that using logic gates. So here we're dealing with the OR logic gate. So let's draw that. Now we're going to have two inputs, A and B. But B, we're going to say is always equal to 1. Now the output will be A plus B. Now let's make a truth table. Now remember, the output will be a 1 if either input A or input B is in the on state. So A could be 1 or 0. B is always 1. So this is B. So if A and B are both in the on state, then this logic gate will be on. So we're going to give it a value of 1. Here, B is on, A is off. So if one of the inputs is on, for the OR gate, the output will be on. So in this case, if A and B are in the on state, we can see that the output is 1. Here, if B is on, A is off, the output is still 1. But this is the one that we're working with. So 1 plus 1 does equal 1 when dealing with logic gates. This means that if A is on and B is on, then the output, A plus B, will be on as well. And that's the way you have to think about it when dealing with these types of Boolean algebra expressions. Now the next rule that we're going to talk about is the complements. A plus A prime is going to be 1. And A times A prime will always be 0. So this is the complement property. Now, using numbers, if you have a 0 and a 1, let's say if A is 0, A prime has to be 1. This is going to be 1. So when dealing with the OR logic gate, if one of the inputs is in the off state and the other is in the on state, the output will be on. So that's what 0 plus 1 equals 1 mean. Now, for this one, we're dealing with the AND gate. So let's draw that circuit. So let's say if we'll call this A and A prime. So if A is on, that means the other one, A prime, will be off. Now, when dealing with the AND logic gate, the only way the output will be on is if both inputs, A and B, or in this case, A and A prime, are both on, because keyword and. Well, this will never happen, because if A is on, A prime will automatically be off. So the two inputs will never be on at the same time. So no matter what, this is always in the off state. So we're going to have a binary number of 0. Therefore, whenever you use an AND logic gate with the A and A prime inputs, the output will always be 0. It will always be off.